Suppose we have a relationship that we want to estimate that looks like this, where y is a function of x1, but then also a function of the square of x1. So we have beta 1 x1i plus beta 2 x1i squared. Erase that dot there. Yep, x squared x1i squared. Sorry about that. So what if we want to estimate this relationship? Well, there's no reason why we can't plug that into our statistical computing software, into R, and estimate. We have one variable as usual, one variable that's just x1, and the other variable we'll just define to be x squared. So we just create a new variable that's the square of x1, and we call it we can call it x2, and we can run this regression. There's nothing that stops us from running this regression. Let's suppose we estimate it, and we get beta 0 equals 10, beta 1 equals 20, and beta 2 equals minus 5. So then we could calculate for different levels of x, 1, 2, 3, 4, 5, 6, what would be our predicted level of y. So our predicted level of y is equal to 10 plus 20 times 1 minus 0.5, which is just a half, times 1 squared, which is just 1. So we have 30 minus a half times 1. So 30 minus a half is 29.5. For our next observation, our predicted level of y is 10 plus 20 times 2 is 40 minus the square, so it's a half times the square of 2, which is 4. So that's 50 minus 2, which is 48. And then just our last one, right, we can have 10 plus 60 minus a half times 9, and we get that. So we can think of calculating all these predicted values of y and thus seeing what the regression line is, the same way we do any regression line. And what we'll notice is the regression line will look like a quadratic. It will rise for low levels of x and then fall for higher levels of x. And eventually, right, if we go back to our estimated equation here, if this is a negative number, if this plus sign is a negative number, so we have minus beta 2, the way we've done it here, eventually this squared term gets larger and larger, right, rises faster than the ordinary x term does, and so the negative will dominate, and so the function starts to go down, and eventually, for x values large enough, the y value would be a negative value, right? Which for some problems is certainly possible. No reason why it has to be always positive. For many values in economics, the return on a stock, for example, can be negative. We have other functional forms too with this quadratic form. If both of the coefficients are positive, then our slope will look like this, our regression line or curve. So now we can think about a regression line that is a curve rather than a straight line. And if we have both negative, then we're going to get something that looks like that, a quadratic downward sloping. So these are the quadratic functions. Now, make sure this, yeah, we can also estimate a cubic function, so we can have x1 to the cubic power. And if you want to visualize what that would look like in R, you can use the curve function, which is part of base R, and then just put in numbers 10, 5, 0.10, and 0.005, and type it exactly the way that I've written it here. From equals 0 to equals 50, and then if you run that, R will draw the resulting curve, and this will be cubic curve, you can change the numbers and draw different curves and see how the cubic looks. If we estimated this relationship, right, we can think about doing a joint hypothesis test that beta 2 equals 0 and beta 3 equals 0. If that joint hypothesis were true, if we couldn't reject it, then we would end up, right, having basically a linear relationship. Only beta 0 plus beta x1 matters, and these two don't matter since we can't reject the hypothesis that the two coefficients are equal to 0. So that's kind of the way we might approach polynomial functions, estimating polynomial functions in R. One last thing we have to think about, which is going back to our standard polynomial function, x and y. So in this polynomial function, y is equal to beta 0 plus beta 1 x plus beta 2x, and in this case, the way I've drawn it, beta 2 would have to be a negative number, right? So beta 2 is less than 0 here, since the slope is declining. Notice that the slope is declining, what I just said there. That is, the slope depends on the level of x. If x is here, we have x1. The slope of the line is pretty steep, but if we're at a point x2, the slope of the line at x2 is flat. So the slope depends on the level of x. Now remember, this is important for interpreting our regression. So to interpret our regression coefficient, we now have a problem, because before we said how much the beta told us how much y changes when x changes. How much y changes? I missed that, sorry. How much y changes when x changes? And that was equal to the slope. But now we see that the slope varies, right? The slope varies with the level of x, and the slope could be positive here, and then here it could be negative. So the effect of x on y depends on the level of x. So we can never talk about a single effect. Instead, we always have to interpret the regression as saying, for this value of x, the slope is maybe positive. So for this value of x, the slope is positive. But for this value of x, going further along here, the slope is negative. So the effect of an increase in x here, when x increases, y goes up. Here, when x increases at this range, and in this range of values of x, when x increases, y goes down. So for some ranges, x affects y positively. For other ranges, x affects y negatively. And there's no reason why functions in economics and in the real world can't have that characteristic. When you eat a lot of delicious food, your happiness or satisfaction goes up. But when you eat a really lot of delicious food, so much that you start throwing up because you've overeaten and you get all gassy and bloated, your satisfaction, your happiness, your utility goes down. So there's no reason why relationships have to be monotonic, always going up or always going down. They can be going up for some values and going down for other values of the x. So this is a pretty common issue, and we've seen how we can estimate this in our linear regression format.